So we talked about PN junction, one of the very basic semiconductor device, and we told how a PN junction is made. You start with a completely p-type or completely n-type semiconductor, and then you diffuse the opposite dopant, opposite kind of impurity from one side in a very controlled fashion, so that it diffuses up to some depth in that material, and at that junction you have one side is p side, one side is n side, and then you have metallic contacts and all those. Then we talked several physical phenomena, that if you have this PN junction, schematically we represent it in this fashion. Put a line here, and this is, let us say, p side, and this is, let us say, n side, and this is that junction. So what we show in the diagram is some small portion of that PN junction, which is actually that semiconductor wafer in which you diffuse things, and it goes like that. But that is how, these are the metallic contacts. From here you connect to the external world. And if this is p-type, you have large number of holes here. You have large number of holes here to start with. And some conduction electrons, minority carriers. Opposite is on the other side, on the n side, n-type semiconductor. Here you have large number of these free electrons, because you have put all those pentavalent impurities, and then you have some holes somewhere, minority carriers. Then we said that because of this concentration gradient, these holes will diffuse to this side, electrons will diffuse to this side, and they will nullify each other. This electron will fill the hole, and then the hole will disappear, the electron will disappear, it will be a bond only. And in that situation, you get this depletion region. There is some region on the two sides of this junction where you do not have charge carriers, right? So you have a region, say, up to here, and then here up to here you have some region where you have no charge carriers. But then the charge density is there. Since these electrons are going to this side, everything was neutral, so you get negative charges here, and then these holes which are going to this side, they create this positive charge here, right? So initially everything was neutral, and then you bring some electrons from this side, you shift some holes from this side, both of them will create negative charge here and positive charge here. So you have rho, charge density rho, which is not 0, but the charge carrier density, that is 0. So this whole region where you do not have charge carriers, that is known as a depletion region. So this region is your depletion region. These holes have gone here to neutralize these electrons, or the electrons have come here to neutralize these holes here, and therefore the charge carriers are not there, that's fine. But then at any temperature, we told earlier that any temperature, new hole electron pairs are created, because in that material you have thermal distribution. These electrons can get energy from the crystal of the order of this Boltzmann constant K times T. So because of that thermal distribution, energies are taken up, energies are given away. So new electron hole pairs are always created, and old hole electron pairs are destroyed in normal semiconductor. So that process is still here in this depletion region also. New electron hole pairs are created, but since you have an electric field here, in this picture we have put positive charges on this side, so the electric field is towards left. So since you have an electric field here, as soon as a whole electron pair is created, holes will be swept away towards left, this side, and the electrons will be swept away on the opposite side. So this region still remains carrier free, right? So that is this. Then we said that, okay, once you have electric field, you will have some potential variation also. In this case, now the potential is decreasing from right to left, so potential will decrease. So this will be at a higher potential, this will be at a lower potential. There will be a potential difference between this N side and this P side. Of course, you have metallic contacts. Again, you have potential difference at this contact also. So finally, if you see from outside, this connection here and this connection here, no potential difference will appear. You cannot light your lamp because of this potential difference that is created. But inside this material, yes, potential difference is created. And if you look at the energy, so the energies are opposite, electron energies, because it's minus E times V. So here the electric field is this side, potential here is smaller, potential here is larger. But if you talk of energies, these energies will be up and these energies will be down. Okay, so let me talk today a relation between these weights, this weight and the potential difference, the electric field and all those things. Let us make some calculation on that. Suppose this width is x1 here and this width is x2 here. So this is the junction line is here. Then this depletion region extends up to depth x1 on this P side, up to depth x2 on the N side, and these x1, x2, they depend on the dopant densities. How many impurities per unit volume you have put here and how many impurities you have put here. So if this is P type, that means you are putting acceptor impurities here, so Na, and here you are putting donor impurities, so Nd. How many acceptor impurities per centimeter cube, how many donor impurities per centimeter cube, that will decide this. If you have large density here and if a smaller density here, and if these holes are to neutralize these electrons or these electrons are to neutralize these holes, a small width is sufficient to neutralize a larger width here, and therefore x1 and x2 will be different. And you can always have this relation rho times x1, rho times x1, rho 1 times x1 is equal to rho 2 times x2. If this is here, rho is equal to say minus rho 1, and this charge density is rho equal to plus rho 2. Then this rho 1 times x1 in magnitude is equal to this rho 2 times this x2, because total charge has to be 0. Total charge has to be 0. Everything is neutral. See, it's only migration of electrons and holes from this side to that side and so on. So the total charge must be 0. So if this is say rho 1, and assume that it is uniform from in this width x1, and this is plus rho 2, which is uniform in this width x2, and then when I am drawing this line, you understand it's a plane, it's a planar area. You have this semiconductor material, and junction is a layer, junction is a plane layer. On one side you have P, one side you have N. So I am drawing on a line, it is in fact a surface area. So that surface area times x1 will be the volume times charge, this rho 1, charge density will be charge here, negative charge, and similarly this volume area times x2 is the volume multiplied by rho 2, that will be the positive charge, and they should be equal in magnitude and opposite in sign, so that the total is 0. This assumption of uniform charge density is not very bad in fact. If I plot rho here and x here, in this case you have negative charge, and in a smaller width I am showing, so it's like this, and this side is positive charge, and I am showing larger width, so it's like this. This is, if we call x equal to 0 here, this is x is equal to minus x1, and this point is x is equal to plus x2. This height here is rho 2 here, and this is minus rho 1 here. And this area rho 1 times x1 should be equal to this area rho 2 times x2. So this step function type is of course an approximation, but not very bad approximation. If this density, this dopant density is uniform in A and in D, it should result this kind of charge distribution. So let me now calculate, if this is the charge distribution, what will be the electric field distribution? How electric field will vary as a function of x. So let me draw another diagram, and I am only now showing you the depletion region. I am only showing you the depletion region. So this is x1 and this is x2, and this is the junction. So up to here you have that negative charge minus rho 1. In this whole thing you have minus rho 1, and in this whole thing you have plus rho 2. And suppose I need electric field at this point at some distance y, which later I will call x, or let me call x, at x, electric field at x. This is x equal to 0, remember, junction is x equal to 0. So at distance x, in that n type side, I am putting a point here. What is the electric field at this point? Okay. So what I can do is, I can first calculate the electric field due to this minus rho 1 charge here, and then I can calculate the field due to plus rho 2. So let's first do this. Let me take a small width here. This is at some distance x, and this is dx. So that charge which is here, this charge, what is the electric field due to this at this particular point? So this you can treat as a surface charge layer, and that surface charge density sigma will be this volume charge density rho 1 and times this dx. Alright, since it is a thin this layer here, I am taking dx, so I can treat this whole charge as on a surface charge layer, and then the total charge will be this minus rho 1 times dx times that area, that will be the charge, and then I divide by the area to get charge per unit area, and that will be this much. And so the electric field due to this will be dE1, let me call it dE1, that will be sigma over 2 epsilon, and it is minus rho 1 dx over 2 epsilon, and this epsilon is epsilon naught times k, and this k is dielectric constant. Right, in free space, in vacuum, or in air, effectively, if you have a surface charge layer of surface charge density sigma, the electric field in front of it is sigma over 2 epsilon naught. Since this is whole thing is in silicon, not in free space, so we put this dielectric constant also, and it becomes sigma over 2 epsilon. Then you integrate from here to here in this entire region, entire width x1, so that dx will be integrated to x1, and so E1 will be equal to minus rho 1 divided by 2 epsilon and then x1. This is the field at this point because of this whole negative charge here. Okay. Then come to the second part, this part. So here let me do it in two parts once again. Let's draw a line here, and this is all plus rho 2. So first calculate the field due to this part, which is to the left of the point chosen. Okay. So once again you can do the similar analysis, and here again you can take a small dx. Again here you can take a small dx. By the way, this was negative charge, and so the electric field that we have calculated, yeah, we have put the minus sign here, so it is in the this towards left. Now this is the width dx I am taking. This dx I am taking. This is now over. This part is over. So this dx I am taking, and once again you can treat this as a surface charge layer of surface charge density plus rho 2 dx, and dE2 will be, again because of this, what is the electric field here? So sigma over 2 epsilon, so plus rho 2 dx over 2 epsilon. So what is the electric field due to this part, which is positive charge plus rho 2 to the left of the point chosen? So what is this whole length? This whole length is, this thing is just x. So E2 is equal to plus rho 2, I am writing from here, divided by 2 epsilon, and then this dx is integrated here to here, which is just x. What remains? This part, electric field due to this part. So let's calculate that also. So this dx is also over. So now let me take a layer here, this dx, and because of this you calculate what is the electric field here and then integrate from this point to that point. So once again you can write dE3. So dE3 will be, the sigma remains the same because this is plus rho 2, so rho 2 times dx. So sigma remains the same, rho 2 dx. dE3 is sigma over epsilon naught, which is rho 2 dx over 2 epsilon naught, but now it will be in negative direction, right? This will be in negative direction because you have positive charges here. You have positive charges here, and you want electric field here. So because of the positive charges, the electric field will be towards left. So we put a minus sign here. So that will be dE3. And when you integrate this and write what is E3, that is the field due to this whole part to the right of the point chosen. Remember, always remember, I am trying to find electric field at this point, which is at a distance x from this junction. Okay, so at this point. So the third part is electric field due to this much, and that will be, when you integrate this, you will have minus rho 2 over 2 epsilon, and then this dx. Now dx, when you integrate, you get this length. And how much is this length? How much is this length? This length is x2 and minus x. x2 and minus x. So it is, E3 will be x2 and minus x. So now I have all three contributions. First contribution is due to this entire negative charge which is sitting here. This is that p-type semiconductor left to that junction depletion layer. So this part here, this part here, This is the depletion region. This is still p type because all those impurities, acceptor impurities are here. So it is that part. So because of this, then on the other side E2 is from that other side of depletion region from here, but only from the part which is left to this point where I am calculating electric field, and E3 is the electric field due to the rest of the system. So this is the thing. Now you calculate what is the total. So the total is, so the total electric field will be E1 plus E2 plus E3, and that is minus rho 1 x1, so minus rho 1 x1 over 2 epsilon naught plus rho 2 x over 2 epsilon naught, and then minus rho 2 epsilon and x2 minus x. And this rho 1 x1 I can write as rho 2 x2 from here. Okay. So this is rho 2 x2. So I can just replace it here itself. This is rho 2 and this is x2. So you see rho 2 over 2 epsilon is common. I can take it out. What is left? Minus x2 plus x, then minus x2 and plus x. So 2 times x and minus 2 times x2. So you can write this, you can put minus sign outside, minus rho 2 over 2 epsilon, because that 2 can cancel. Okay, and then you have x2 and minus x. Since x2 is greater than x, that's why I am writing x2 minus x and a minus sign here. So if I plot for electric field, here is the plot for charge density. If I make a similar plot for electric field as a function of x, taking towards right as the positive, how will it look like? It will be like this. Now I am plotting this E here, and this is x. This is the point x2, let us say, and this is that point minus x1. And I have calculated for this region only. This is negative, so this electric field will be on the negative side. At x equal to x2, the electric field will be 0. So here the electric field will be 0. And how much will be electric field at x equal to 0? At x equal to 0, E will be minus rho 2 x2 over epsilon. So it will be somewhere. It will be somewhere. This is the point. Let us say this is minus rho 2 x2 over epsilon. And then it is linear. Then it's linear. It's linear in x, so it has to be a straight line. And therefore you can join these two. This is the electric field. This is the electric field on this positive x side. You can do a similar calculation for electric field in this region, this part. You can do a similar calculation here, and you can just guess what it will be. When I did this, I get electric field at this x equal to x2 as 0. Do exactly similar analysis and you will get electric field at this x equal to minus x1 as 0. So the electric field will be 0 here, and so this is for x less than 0. This was for x greater than 0 in the depletion region, remember. After the depletion region, after x2, there is no electric field, and this electric field just goes like this. And on the other side, for x less than 0, what you will expect is that at x equal to minus x1, the electric field will be 0, and the same expression here at x equal to x2 electric field is 0. So, at equal to x minus x1 it will be 0, and then at x equal to 0, from the same expression if you go, your electric field should be minus, it was rho 2 x2 here, so it will be rho 1 x1 here divided by epsilon, but it's same as this because rho 1 x1 is equal to rho 2 x2. So, it's same. It should be, and therefore, the electric field will be like this. So, this is how the electric field will appear. It will be linear in the two regions. Depending on the dopant density, you will have a certain slope of this E versus X line here and here. So, our next task will be to calculate the potential as a function of x. Once I have electric field, I can calculate the potential using our equation E is equal to minus dV dx. So, we can calculate this potential as a function of x, and from there energy as a function of x, and from there the potential barrier. So, that will be our next task.